Close your Chromebooks. We got a new lecture today. Today. Okay. So close them up. What we have today? We are going to start the next section of the volcano chapter. So we're talking about volcanoes. Again, the Iceland volcano is still. I didn't mean to turn that back on. My bad. The Iceland volcano is still erupting right now. It's been spewing out quite a bit of lava for a while, so it's in Iceland doing its thing. It's actually pretty interesting to watch because, on the live stream, you can just see how much lava is bubbling out like every single second. And so this has been going on for weeks now. The trail of lava goes way down the hill, and people are out there all the time, kind of doing science and trying to understand a little bit more about what's going on and get some data. This doesn't happen every day, and it's not super often that it happens where it's nice and quiet and like an easy, non-violent explosion. And so it's just sitting here kind of bubbling out, and it allows you to do some nice science.
Is that still hot?
Oh, yeah. Some of it is cool enough where you can walk on it and get close to the lava, but some of it's still going to be very hot. And it could take, it could take decades or like hundreds of years for some of it to cool down because it gets trapped underneath inside the rock and it gets really hot, and that heat takes a long time to dissipate. So
how far can you be away from it? Like, can you feel the heat?
So we're actually going to watch a little video on that. Yes, you can feel the heat. It depends on how much lava is exposed as to how close you can get to it and kind of the direction of the wind. But there's a video that we're going to watch in just a second about a guy who's trying to get really close to like a volcanic eruption. You can see the lava there. And they were talking about how he had to deal with how difficult it is to get up close to that heat. So yeah, this is going on right now. There's a lot of little videos you can watch of them flying drones around it. But today, we're going to talk about the types of volcanic eruptions. So how do volcanoes erupt? And in general, we're going to lump everything into two categories. There are explosive eruptions and non-explosive eruptions. And in general, you can lump everything into one of those two very broad categories. So as we go through this, I'm going to kind of divide everything into two separate groups. And there will be lots of little divisions. So based on like what minerals your lava is, what the shape of your volcano is, how often it explodes, there's lots of different things to look at. So they start off on page 1, actually, if I go back to engage. And they go over the two basic types of eruptions and the volcanoes that we can kind of associate with that. So this is a really short video. It's just about Mount St. Helens. Oh, wait, hold on. Let me switch my speaker over. There we go. And can we play? Maybe. Maybe not. It's working. Or is it working? Cool. There we go. Okay, let's try to reload the page. See if that works. Oh, it won't. But if this doesn't work, it's not a big deal. It's just a short little video. Okay, I guess that video is not going to work. But basically, what happens in 1980, Mount St. Helens erupts. It starts to show a little bit of activity. On May 18th, there's a earthquake that triggered a landslide. Whether the earthquake triggered the landslide or the volcano triggered the earthquake, it's kind of like which comes first, the chicken or the egg. But there was an earthquake. Half the mountain collapsed, so literally like one side of the mountain caved in a huge landslide, and the volcano erupted in a huge explosion with a giant ash cloud going down the side of the mountain, traveling over 60 miles per hour. knocking down hundreds of thousands of trees, flattening everything in its path. There was a giant flood of ash and mud, so like a instant flash flood coming down the mountain. Destroyed a bunch of stuff, killed like, I think it might have been like 62 people. There you go. Killed 62 people and caused millions of dollars of damage. So your Mount St. Helens eruption, or if you think of like a volcano like in Japan, Mount Fuji, those are your classic violent eruptions. Like the whole mountain blows up, ash, smoke everywhere, very dangerous. You don't want to be near it at all. The opposite end of that are the Hawaiian eruptions. And this one is actually going to hurt, so.
Every few years on the island of Hawaii, nature puts on a dazzling show. Red-hot lava erupts from deep within the earth, exploding high into the sky in fiery displays. And then it rushes downhill in rivers of fire. When it reaches the ocean, the lava cools immediately, sizzling and splattering, exploding, before it hardens into rock, becoming new land. All of the Hawaiian Islands were formed in this way. Of all of Earth's forces, none are quite so spectacular or so important to the regeneration of our planet.
Okay, so real quick, you don't want to be standing right next to this, right? It's if you get lava on you, it's not going to be a fun day. But they're also not worried about this entire mountain exploding. This is, you can see that the camera's not too far away from the lava. They have people that can walk right up to those lava rivers and take samples from them. And so these explosions, while I still have a lot of lava coming out, I'm not afraid that the whole volcano is going to explode and cause a huge problem for me. Yeah.
So like, say like a little tiny drop, just like not on your skin will happen.
You're going to get a burn like right on your skin. In the same way that, let's say you were out in the welding shop and you're welding without gloves and like a piece of metal falls on your skin, like a molten piece of metal, it's going to burn you right there. It's not going to like burn through your entire arm or anything, but it's probably going to instantly like sear your skin, and you're not going to have a fun time for the
What's
rest
that
of the day.
movie? Where, like, lava is running through the city?
I don't know.
No, it's not Pompeii. It's like,
There's a lot of volcano movies.
no, it's like,
That's just movie.
What's the name of it?
Twin Peak, I think.
One Peak?
No, Twin.
Oh, Twin Peaks.
yeah, and then it melts. So that's not gonna, you're not gonna melt like that.
The guy melts? No. Often the things that happen in the movies aren't exactly how
Would
it's
you
going to
just
happen.
catch on fire?
Uh,
Like with your clothes and stuff like that?
I don't know. I mean, so listen, you're basically going to get severe burns on the vast majority of your body. That's actually something that's happened recently down in, I think it was New Zealand, the island nation near Australia. There was a cruise ship down there. They had a volcano that you could go and tour. The cruise ship took an excursion of people into the volcano for the tour. Literally, while they're in the volcano, it erupts. Several people die, and a couple people get essentially like volcano first-degree burns over the vast majority of their body. Yeah, they survive, but like not in like a good way. Yeah, and so it's pretty bad, but they do have instances of people getting burned by lava. They have instances of people falling into lava, unfortunately. I don't think that's happened a lot, but it has happened. So we only got a couple seconds of this left. We'll see what they finish off with. That's it. All right. So keep that in mind. We have explosive volcanoes, and the explosive volcanoes are going to look like your classic volcano that we imagine. It's going to be a big mountain peak. It's going to have a crater on top, and even sometimes you get your snowy peaks up top where you have snow on it. That classic look volcano, those are called composite or stratovolcanoes. and they are the explosive ones. So these are the ones that are going to explode. When you talk about volcanoes like Hawaii, those volcanoes don't look like the classic volcano. Those volcanoes are called shield volcanoes, and they basically look like a big hill. And if you've ever seen Hawaii as an island, this whole hill right here is almost the entire island of Hawaii. It is the volcano. And so they're very, very big. These are not drawn to scale. This volcano would make this one look like a tiny little hill. These are absolutely huge. The area where it erupts in the center is just like one little hole, but it's usually like a mile wide. And the lava is very runny here, so it will build up and like run all the way down into the ocean like we saw in the video. And so that's what builds up this giant hill here, is all the lava running down into the ocean, layer after layer after layer. But these are very big. These are called shield volcanoes because the shape of the top is like a shield, kind of. So the example of this would be Hawaii.
But is it always shaped like a volcano for it to explode?
And they're non-explosive. What's up?
Or never mind.
No, which one? You talking about this one?
Are they always like that?
Yes. In general, they're going to look like a mountain, like we imagine mountains and volcanoes look, and they're going to be explosive. They don't all have to be explosive, but the way that they form makes it more likely. And here's the problem. What happens on these volcanoes? What happens on these volcanoes is it will get stopped up. Like the lava is very thick and viscous, and it doesn't flow very well. And so it's almost like trying to squirt like honey through a straw. It's not going to work as well as like water through a straw, right? Because the honey is very thick. You try to blow it through, and it's not going to go through very quick. And so what happens with these volcanoes, somewhere in this neck, it gets clogged up. The lava doesn't want to move. It gets stopped up. It gets backed up. And I build up a bunch of pressure inside until eventually it all blows out the top. Or like in the case of Mount St. Helens, it just blows out the side of the volcano and blows the whole thing up. The Hawaiian volcanoes, the lava is very runny. Almost, it's not like water, but closer to water than to like honey. And so when it comes up, it's never going to get clogged up. It doesn't get clogged up. It doesn't stop running. It just comes out. It might spew out a little bit at the top, but it's not like explosive. It'll just squirt it out. It falls back down, and it runs out to the edge of the sea. And so that's why some are explosive and some are not. It's how thick your lava is. Yeah.
So, like, a volcano is a hole in the crust, correct?
Yeah.
So, how does it eventually close up? Wouldn't it just keep...
The reason you have a hole in the crust is because you have hot material coming from the bottom to melt that hole. Yes, but so it is coming up. It is essentially coming up through the crust, but the crust is much thicker. So like if this is the volcano here, the crust ends like way underneath the board. And so yeah, it's kind of like a hole in the crust, but I need like a bubble of like that hot magma to come up and feed my volcano to come up through the crust. And so as soon as this runs out of magma, then my volcano stops erupting.
Does the crust close back up? Like after that magma goes away?
No, these bubbles will just kind of come up somewhere else. And so it's always moving in different ways. But really when you get into like what the mantle is doing, how it moves, and what happens when a volcano dies, we still have multiple theories about that. Geologists are still arguing on like how that stuff moves underneath the surface. Because we can look at it a little bit using seismic waves, but we can't go down there and actually see it. And this stuff moves very, very slowly. And so we've only been looking for like 20, 30 years, studying what's actually underneath the earth in a real like scientific way. And that's just like a blink of an eye. So we don't have the fullest picture yet. But we're building new pieces every day. So they start on page 1 with magma composition. And we talked about this a little bit in the first section of volcanoes. The idea is your magma felsic or is it basaltic? Does it have a lot of silica or does it not have any silica? That's going to determine how thick it is. And so the really thick, viscous lavas that don't flow very well and cause massive explosions because they stop up the volcano, they have a lot of silica. Silica doesn't like to flow. It doesn't like to melt. It doesn't form that nice, easy, like flow, like water kind of thing. It's very thick. It's going to flow like plastic. It's going to plug up all your holes and keep your volcano from erupting easily. It's going to make it explode. So if I have a lot of silica, I have a very thick felsic magma. It's not going to flow very well. If I have low silica, like my mafic rocks or my ultramafic rocks, they're going to flow very easy. That's the lava that I can just let out of the hole right in the middle of Hawaii, and it's going to roll downhill all the way to the ocean and form some new rocks on the side of the ocean there. So let's see what else we have. Viscosity of magma, we've already touched on this. Basically, the higher the viscosity, the thicker it is, and the harder it's going to be to flow. Think of like pouring syrup out of a bottle. You can tip the bottle over, but it all doesn't fall out instantly. It takes a second because the syrup's very thick. Syrup has a high viscosity. So when my lava has a high viscosity, it's going to flow very slowly in like big chunks. If it has a low viscosity, it's just going to spread out like water and flow wherever it wants to go. Not quite like water, because water is very, very thin, but that's what we're looking at. And then they rate the explosiveness with the eruptions, which we've already done also. The higher the viscosity, the thicker it is, the less likely it is to easily flow out of your volcano, the more likely you are to build up pressure and have an explosion, where your whole volcano explodes. If it's nice and runny, it's just going to flow out of the volcano and go wherever gravity takes it, and there's not going to be any explosions, and it's not even really a big deal. Maybe Hawaii comes and tells you, hey, you got to move out of your house within the next 2 weeks because the lava's coming. So we do have two different names for types of lavas, and they'll probably ask you questions about this. Note that in geology, we try our best, and we fail sometimes, but we try our best to use names that make sense to the people that actually live in these areas. So when we talk about volcanoes, the people who have lived their entire existence around and on volcanoes are the Hawaiians. And so when we name volcanoes, we try to use names for terms that the Hawaiians have created and not just make up our own new terms. So we have two types of lava, and both of these are Hawaiian names. One type is A'a. It's literally just two A's, and you say them both A'a. The other one is called Pahoehoe. So Pahoehoe is your ropey lava, like you see in the videos a lot. And A'a is like big and blocky. It almost looks like a pile of dirt with lava inside of it. So this is actually both of them. The ropey stuff that looks like it flows downhill really easily and sometimes gets like a hard crust on it, but you still have lava underneath. This at the bottom part is your Pahoehoe. That's the classic lava that you see in the videos a lot. This stuff at the top part, this isn't a great picture. This is your A'a. It's just the two A's, and basically when this stuff is around, it looks like a giant pile of dirt with lava mixed in. And so it's big and blocky and chunky. It doesn't flow very easily. It basically moves like a bunch of sand instead of like a bunch of water or honey. Yeah.
That layer on top of the lava right there.
Yeah.
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 Is it like a skin or is it like a rock?
Well, it depends on how long ago it erupted. It's like a rock skin, basically. So it could be very thin, or if you poke it with a stick, you go straight into straight lava. If it's been here for like a couple weeks or a couple months, which it probably hasn't because I can still see this is hot. But if it's been here for a while, it'll be solid rock, and you poke it and it won't break through. But yeah, right now, judging by how hot that is, if I poke that with a stick, it's going to go straight through and I'm going to have lava underneath, which is why if you go tour these places in Hawaii, you got to listen to your guide, because you step on the wrong thing, your foot goes through and it's in lava, it's not going to be a good vacation for you the rest of the time. But yeah, it really depends on how long it's been there and how much it's cooled. So, talked about Pahoehoe and they talk about pyroclastic materials. This is just the stuff that happens in an explosion. So when we say pyroclastic, we mean my mountain is blown up and it's throwing stuff up into the air. And so you can have ash, you can have chunks of rock, you can have volcanic gas. All of these things are part of the pyroclastic materials that comes out in your big explosion cloud. So I go through a couple different types of pyroclastic materials. They do have some names for different sizes. So like lapilli are little small balls around 2 to 64 millimeters in diameter. They're going to be made up of like rock or lava. So like pea-sized or a little bit bigger, not too bad, maybe walnut-sized. Or you can have things as big as blocks or bombs, which here they are. Blocks or bombs are basically large chunks of rock that the volcano throws out. Big enough to kill you for sure. And if that weren't bad enough, some of them, which are called bombs, are basically like what we just talked about. A thin skin of rock on the outside, but the inside is still molten lava. And so it's like a projectile, like a lava water balloon in a way. When it hits, it's going to explode and throw molten lava everywhere. And so these things get kind of crazy when they erupt like that. So you can see a couple sizes here. Little lapilli-sized pieces, roughly pea to walnut size. Your ash, or it can throw up big blocks and bombs. What else do we have? So they go through the volcano types in this video. Let's watch this real quick.
The volcanoes of the Ring of Fire are stratovolcanoes, including Mount St. Helens.
So that's your classic volcano. These are the explosive ones. They're the ones that get kind of clogged up before the erosion or the explosion happens, builds up pressure, and then eventually it just blows its top.
And Mount Fuji in Japan, as well as Mount Etna. These volcanoes can explode violently with deadly results. When two plates converge, the subducted plate carries sediments and gases into the mantle, and when it melts, the magma is more viscous, trapping the gases. As the magma approaches the surface, the pressure decreases, causing the gases to expand. That rapid expansion propels the magma through the hard crust of the volcano's cone, often creating an intense explosion. This is what happened in the Mount St. Helens eruption in 1980. The eruptions of these types of volcanoes are often a mixture of fiercely hot toxic gases and lava that flows down the sides like an avalanche at phenomenal hurricane-force speeds, often over 100 kilometers per hour. Stratovolcanoes that have viscous lava have cones with steep sides, because the lava hardens quickly after it flows out of the vent. Hotspot volcanoes, such as those in Hawaii, erupt basalt lava, which has low viscosity and flows downhill quickly.
So that's your Pahoehoe. You got like the hard crust on the outside, but you can see it's just like molten lava inside.
Making a large cone with gentle slopes. These are called shield volcanoes because the cone has the shape of a shield. Lava dome volcanoes are relatively small. Their lava is too viscous to flow any distance, and it piles up around its vent. Cinder cone volcanoes are formed from particles of lava that are ejected from a single vent. The lava falls in fragments around the vent to form a circular cone. They rarely grow more than 400 meters high. Volcanoes give us a glimpse of the power of Earth's fiery furnace.
Okay. So, real quick, there is a third one that she mentioned. It's just a tiny little cinder cone volcano. They're really small. They have the shape of a regular volcano, but they're smaller, and it's mostly just ash. You can find a couple of these in like Arizona, New Mexico-ish areas. And they're pretty small. You could climb it in like an hour or two and get to the top and come back down. They're not super big or explosive. What are you gonna say?
I was just gonna say, how big have you been in one before?
Oh, small enough. I've seen one, but I've never climbed one. Yeah, they're not too big. Like a big hill. No one would call it a mountain or anything like that. So let's see what else we got. They talk about each of the volcanoes, so they give you some details about shield volcanoes, composite volcanoes, and then there's cinder cones, and they even have calderas and lava domes and fissure eruptions down here. Let's see. Volcanoes as a constructive force. So one of the things we try to do in geology is point out the good things and bad stuff. So when volcanoes erupt, that's generally bad. But, without volcanoes, we wouldn't have Hawaii, and Hawaii's awesome. And that's like 100% volcanoes. And so one of the good things about volcanoes is it does build land for us. It adds new land. It builds islands. It adds land onto the side of our continents. Volcanoes help keep us above the water. Another good thing that volcanoes do, they bring a lot of nutrients to the surface in these soils. And so volcanic soils actually grow some things that we like a lot better than other soils. For instance, pineapples grow great on Hawaii. I think coffee is traditionally grown in volcanic soils. It grows really, really well in volcanic soils. So if you like coffee, you can thank volcanoes for how well it grows. And there's a couple other crops that just do really, really well on volcanic soils instead of regular soils. Volcanism as a destructive force, obviously it will blow up your town or your city if you live near a volcano. It can cause floods and ash falls and mudslides and all sorts of other, gravity events where you have mass wasting and a whole bunch of land sliding down a hill. What else? Obviously, the lava can destroy things and start fires. Your ash can destroy crops and mess up airplanes and car engines and all sorts of stuff. We've never really had to live through a modern day ash fall, but it's not good to drive your car or airplane or helicopter or anything through ash. Your engine's not going to get the proper amount of oxygen to fuel. So yeah, all sorts of little destructive things. And I think that's the last page. So tomorrow, what time is it? 7:15. 15 minutes. Let's do it. Let's do a sign. Yeah.
I think we should go to a lot of videos of volcanoes. I was interested in that.
Let's go down. We're gonna do the constructed response, but which one? They got Spanish versions. They got types of volcanoes.
The Spanish one.
So types of
They got types of volcanoes. Well, what's the difference between those two? Maybe they're the same. I'm just gonna pick the top one. Assign it today, Tuesday. Earth and Space class. And let's see what it says. So this is up and assigned now. It is 6 questions. Nice. Look, they have like a whole little paragraph for you to read. They have what looks like some ash maps, which is nice.
Cool.
Ash maps. What was the impact of the eruption on light penetration? Why did the average temperature change after the eruption in June 1991? How far did the impact of this one volcanic eruption extend? What can you infer about the particulate content of Mount Pinatubo eruption? What impacts do you think this could have on travel? During Earth's history, volcanic eruptions with plate tectonic movements have produced many massive volcanic eruptions. In what ways could this impact the composition of the Earth's atmosphere, the Earth's climate, and living organisms? All right, the last one's a little long, but let's check it out. So what they have here, they give us an explanation about the volcano they're talking about. And so they're talking about Mount Pinatubo. In general, They say volcanic eruptions release ash, steam, carbon dioxide, sulfur compounds into the atmosphere. These products of an eruption stay in the atmosphere for varying times, depending on their particle size, density, and the height they reach in the atmosphere. So they're talking about what volcanoes put in the atmosphere and how long it stays there after an eruption. Sulfur dioxide and sulfur oxide form light-colored particles that are very reflective. If these compounds reach into the stratosphere where the air is very dry, they can take a very long time to form a large enough particle to precipitate, which precipitate, like precipitation means rain, so it's coming out of the atmosphere. Because sulfur compounds are so reflective, they can block some of the sun's energy from reaching the earth, causing the climate to cool. Thinking back to some of the questions we read through, that's what they're going to ask us about. Optical depth is a measurement of how much absorption takes place when light travels through something. It can be used as a measure of how far the sun's energy can penetrate into the atmosphere. The bigger the optical depth, the less light penetrates to the Earth's surface. After the eruption of Mount Pinatubo in the Philippines in 1991, the optical depth of the atmosphere changed in significant ways. Global average temperatures decreased by almost half a degree Celsius that year. Using satellite images, help answer the following questions. Note that dark shading indicates low light penetration and white indicates high light penetration. Does that make sense? Dark areas are where I'm not getting very much light. Light areas are where I'm getting more light. And they don't include the Arctic circles here. Those are just the Arctic circles. So, what are we looking at? What's the first question? What is the impact of eruption on light penetration? So they're showing here, do they tell us when it happened? So December, April, June, July, August, September, December through January. And I'm assuming this erupted, it says 1991, but I'm assuming it erupted in April of 1991. So what I'm seeing here is that right away after the eruption, you have most of the northern hemisphere getting less light. There's a couple patches in the southern hemisphere, but in general, it looks like going all the way around the world in the northern hemisphere, you are getting less light than normal because of this eruption. What was the impact of the eruption on light penetration? And I would say this interruption lasted for what? Half a year at least. We're going to December from April. That's like 3/4 of a year. So I would say if you're including April, that's 9 months.
This
Yeah.
is 93 though.
What? Wait, what says 93? Oh yeah, these are different years. So actually, thank you. These are different years. 91, 91, 91, and then this last one is several years later, December 93 to 94. And so it is starting to clear up a little bit, but it looks like it doesn't go all the way away for another 2 years at least. So I would say for a couple years it changes the light penetration. So what was the impact of the eruption on light penetration? It reduced light penetration, especially in the northern hemisphere, for probably close to 2 to 3 years. What did the average temperature change? Why did the average temperature change after the eruption in June 1991? Why would the temperature change? What were we just talking about in question 1 that would make the temperature change? Because what?
Oh, there was no light. So.
Yeah, you're getting less sunlight to the surface from the sun because the ash cloud is blocking it out. And so I would say something along the lines of the ash is blocking out energy that we normally receive from the sun, and so that makes the atmosphere cooler. The ash blocks out energy from the sun, making the atmosphere cooler. How far did the impact of this one volcanic eruption extend? You can see it right here, all the way around the world in the northern hemisphere, and even some into the southern hemisphere. So This affected most countries and continents in the northern hemisphere, and some in the southern hemisphere, is what I would say. All the way around the Earth. So this says, what can you infer about the particulate content of the Mount Pinatubo eruption? Well, if we go back to what we read up at the beginning, there are two main things we can infer because it blocked out a lot of sunlight. We can guess that it had sulfur oxide and sulfur dioxide. And we can guess that they stayed in that stratosphere. They talk about those being in the stratosphere and how long it takes them to leave the stratosphere. So we can assume that they got into the stratosphere and stayed there for several years, blocking out sunlight. So we know because there was sunlight blocked out that there had to have been sulfur dioxide and sulfur oxide. Those are the ones that block out sunlight very well. And that they probably got into the stratosphere and stayed there for several years, blocking out sunlight.
What number is that?
That's number 4. So what we're seeing, because we see the sun blocked out, we know that the ash that came out of the volcano had sulfur oxide and sulfur dioxide, and that it stayed in the stratosphere for several years, blocking out the sun. In the stratosphere. What impacts do you think this could have on travel? What's a lot of ash in the air going to have on travel? What's that going to do? Yeah, it's going to restrict travel. It's going to make flying airplanes much harder to do, and it's going to affect people vacationing in the northern hemisphere. Who wants to go on a beach vacation if I know there's not going to be any sun and there might be ash literally falling from the sky? That doesn't sound like a great time on the beach. And so yes, it's gonna affect airline travel and flights, and it's gonna affect tourism. And then number 6, during Earth's history, volcanoes associated with plate tectonic movements have produced many massive volcanic eruptions. In what ways could this impact the composition of the Earth's atmosphere, the Earth's climate, and living organisms? I mean, it's basically just putting everything that we just said together into one sentence. The eruptions can add gases like sulfur oxide and sulfur dioxide to the atmosphere. Those gases can block out sunlight. The lack of sunlight can change the climate. And then what else were they asking about? Just leave them on the story. Climate and living organisms. And obviously, any change in the climate is going to affect people and other living organisms on the planet because we all live in harmony with the environment. Yes. And make sure you hit submit. This is my class full of seniors, so if you're hovering around that failing passing mark, every single assignment needs to be turned in. Every question needs to be answered. Don't cause yourself a summer of makeup work for not just doing 1 or 2 assignments. You got what? 4 weeks left? Seniors, maybe 3. You take out stuff, yeah. So make sure you're getting these assignments in. Pad your grade as much as you can. Make sure you graduate. Yes. Yes.